Hello everyone, welcome to COMP125, Principles of Computing. In this video, we are going to start our discussion about algorithm efficiency. So after you learned about this chapter, you would expect to know about different attributes of the algorithms and not only the definition that we have already seen in previous chapters. You would learn about four new important attributes about algorithms and why they are important for us. You would learn about the efficiency of the algorithms and how we can analyze the efficiency of different algorithms, and you would learn it through some important algorithms like sequential and binary search, selection, sort, data cleanup algorithms, and pattern matching. So in fact, we will actually analyze these algorithms, and through these algorithms, you will learn about how we can analyze the efficiency of algorithms. You will also learn about this new term, orders of magnitude, and the growth ratio of different algorithms. And at the end, we will also cover this term intractable problems and this fact that some problems we cannot find efficient algorithm for them. They would actually take a long time to solve them. Okay, so first I'm going to discuss some attributes about the algorithms. Remember this definition from the about the algorithms from the first chapter. So this is a definition. This is not talking about the attributes. So if you write an algorithm which doesn't actually follow these rules, this is not an algorithm. So let's just review that. So an algorithm is going to be a set of operations that they are well ordered, they should be unambiguous, and they should be computable. So it should be clear that what is the meaning of each operation. The order of executing them should be clear, and they should be computable for the computer. So computer should be able to compute them, and we should after actually they get executed, they should produce a result, and they should finish in finite amount of time. They should stop after a finite amount of time. So if any of these rules is not followed by a set of operations, that's not going to be an algorithm. But just actually following these rules is not going to give you a good algorithm. When we wanted an algorithm, that algorithm should be actually working. There are some other attributes that we care about. The first thing is that although in this definition, we said that the algorithm should produce a result, okay? But the thing is, we just don't care about producing a result. We wanted to make sure that the result is correct. The result is in fact, the answer that we expect. That if you write an algorithm that doesn't give you the correct answer, that's going to be useless algorithm. Not only useless, in fact, it can be very, harmful. It can actually cause us some harms that you cannot actually cover up. The next actually important attribute is that your algorithm should be clear. I will actually explain each of these attributes one by one, which basically means that it should be understandable by others. You shouldn't write an algorithm that you are the only one who can understand it. So the algorithm should be clear and understandable for other people who are going to use it. And the other actually attribute is going to be the space and time efficiencies. So these two are referring to the fact that your algorithm should use the resources, both space, it means that the amount of memory that your algorithm will use and how much time it would take to be executed. Both of these two should be, both of them should be optimized. So we care about the optimization of the space and the amount of memory that you use and the amount of time. So these attributes that I wrote here, not only they are important, the order of them is also important. So the most important attribute for the algorithm is that it should create the correct answer. Then after that, actually clarity is going to be important, and then after that, the efficiency of space and time. So correctness, this attribute is quite clear. When you write an algorithm, you don't want to write an algorithm that doesn't produce the correct answer. Your algorithm should produce the correct answer. So your algorithm should produce the correct answer for all the inputs that you pass through it. We know that some problems are going to be, in fact, very difficult to solve, and sometimes it's not possible to find the exact solution. So, for example, when you are looking, just think about it in this way, that the answer for some problem is going to be the number p, right? You know that the number p is going to be something like 3.1416 something. So this is something that, finding the exact solution is not possible, but we might actually just define some level of the accuracy and say that, okay, if you find some answer like 3.1416 is going to be enough, although this is not the exact answer, but it actually has some degrees of the, some precision degree, right? So this is the first important attribute of the algorithms that we care about. The next actually attribute is clarity. When you write an algorithm, it should be easy to read. When someone else is going to come to read your algorithm, it should be readable for them. This is important because most of the time, the one who wrote the algorithm is not going to be the one who is going to always use it. You write an algorithm, and this algorithm might be used by many other people. So they are going to use it. Later on, they might actually need to add something to that. So your algorithm should be clear enough for other people to understand it. So the cost of maintenance for the algorithm is going to be lower. Right, so the clarity is going to be the second important attribute. Something here that is actually another attribute for the algorithm, which is not as important the others, is going to be the elegancy of your algorithm. Let me actually just give you an example. This is in section 2. I don't know what's going to be the page number in your textbook, but in the version that I have, this is going to be the page 94 and 95. This example has been explained, so I'm just referring to that because I wanted you to read it completely in your textbook. So just assume that we are interested in calculating the summation of some numbers from all the integer numbers from 1 to n. Okay, so far we know that we can write an algorithm that just add up all of the numbers, all of the integer numbers from 1 to n. So I can write an algorithm that it can be done using a loop, right? You can actually just start a loop, the value of I, which is taking different values from 1, and then it became 2, 3, until it reaches to n, right? And you add all of these numbers together, so at the end, sum is going to actually show the value of this summation, right? But instead of writing an algorithm like this, you know that actually Frederick Gauss has invented a formula for the summation of integer numbers from 1 to n, and that formula is in fact very elegant. It actually just tells you that you don't need to add them all. You can just follow this formula that the summation of the integer numbers from 1 to n is going to be n to n plus 1 divided by 2. So instead of going through this loop, you can just use this formula and calculate your summation very fast, and it actually looks great. But the thing is, when inside your algorithm, if you write this formula, or if you write this pseudocode to add the summation of numbers from 1 to n, this one is more elegant, right? This is actually very smart, but this one is more readable. So always, in practice, there is a trade-off between the elegance and the clarity of the algorithm. Sometimes if you write something more clear, this is going to be less elegant. But sometimes if you write something in an elegant way, this is going to be more efficient, and you can actually just, if you write a formula like this, for example, this is going to be less possible that you make a mistake in calculating the summation than you write, this algorithm. So although such an example is not a great example to explain it, but this is the example from your textbook. So, and I think this is quite understandable what is the fact here, that the elegance, the conflict between elegance and the clarity. Sometimes you might actually just decide to go with the elegancy. Sometimes you might actually choose to get to write a more clear algorithm. And the last attribute, which in fact is going to be the focus of this chapter, the rest of this chapter, we are going to focusing on efficiency of the algorithms and how to analyze the efficiency of algorithms. So something that we actually care here is that is your algorithm using the resources of the machine properly, efficiently? The resources are going to be a space, which is going to be the amount of memory that your algorithm is going to use, and the time, that how long your algorithm would take to be executed. So in terms of the space, this is going to be, so for example, if the input to your algorithm is going to be a list of numbers, that we don't mean that how much space that list is going to take, because that's going to be the initial data or the input data. So except the initial data and the input data, how much other space your algorithm is going to take. This is important for us. Of course, you would actually prefer some algorithm that takes less amount of memory, right, than over an algorithm that takes more space. Of course, you would prefer an algorithm that actually gets the work done in less amount of time. It actually executed faster, right? So the rest of this chapter, we are going to focusing on the efficiency of the algorithms. And before we actually cover the analyzing the efficiency, we should first define how we can actually measure the efficiency, right? So I'm going to just talk about this some tools to measure the efficiency of the algorithms, and I'm going to explain it through an example. So the most important thing that we are going to focus here is going to be the time efficiency, which means that how much time your algorithm would take to be executed. When I'm saying how much time, I don't really care about the exact amount of time, because the exact amount of time of executing an algorithm depends on many different things. It depends on the machine that you are actually running it. If I have a faster machine, definitely the time is going to be less, right? If I have an older machine, it's going to take more time. So this is the exact amount of time is not important for me. But when I'm actually talking about the efficiency, the fact is, for example, I have a couple of algorithms and I am going to choose between them. Which one is going to be better? So are you going to, for example, run them on a machine and check that which one is going to work faster? So is it going to be a good option? The answer is no, because the result of such a comparison is going to depend on a lot of different factors. So on which data your algorithm is going to be executed. The input to the algorithm can be, in practice we might have infinite number of different input. So which one you are going to choose to try your algorithm? You cannot go forever and try all of different possible inputs, right? This is not possible. You should just probably choose some benchmark, but those benchmarks are not going to help because they are not going to cover all of the possibilities. So running your algorithm on a machine and just timing it is not going to be a useful approach to compare the efficiency of the algorithms. The other actually issue here about the timing of execution is that maybe if you run your algorithm on an older machine, you get a different result than when you are actually running it on a newer machine. I mean, when you are, for example, running your algorithms on an older machine, maybe the second algorithm works better, but when you are actually comparing it on a faster machine, you will see that the first algorithm is going to work better. And it is possible. This is completely possible depending on the algorithm that you have written. So the exact timing is not going to help us. So the main fact which is important and we care about when we are analyzing the efficiency of our algorithm is that how much work your algorithm is going to do, how much work your algorithm needs to do to finish, to be executed. By how much more work, we don't mean the exact time, because so for example, if you have a machine that execute like 1,000 operations in 1 second, this machine is going to take a specific amount of time to execute your algorithm. If you have another machine like that actually execute 1 million operations in 1 second, this machine is going to be faster, right? So I don't care about the exact time. If I know that how many operations your algorithm would execute, so I would always know that okay, this algorithm that needs less number of operations, less amount of work, is going to work better. So it doesn't matter if I run it on this machine or if I run it on this machine. So we are going to abstract away these details of the machine that you are going to run your algorithm on. Okay, and just think about the essence of your algorithm, how fast your algorithm is going to be executed. If your algorithm needs less amount of work to do, your algorithm is going to be faster, right? Less amount of work is going to be the number of steps, the number of operations that your algorithm will execute. So this is something that I'm going to actually discuss it and show it to you through an example. And that example is going to be the sequential search algorithm. You have seen this algorithm from in chapter 2, so I'm going to review it again here, and we will see that how we can actually measure the efficiency of the sequential search. So let's actually just review this problem. Okay, in searching, in the sequential search, we have you can actually just think about it in this way, that you have a list of values, that list is completely random, and you are looking for a specific value that we call it a target value. Okay, so what does the sequential search do? Sequential search will just get the target value and compare it with all the numbers in the list one by one. So until it actually finds the target value in the list, or it reaches to the end of the list and say that, okay, I could not find the number. So this is the algorithm, the pseudocode from chapter 2. We just actually repeat it here. So as you can see, I have, in that actually algorithm, we had a set of phone numbers and some names associated with them, and we had a target value that which was actually a specific phone number. We wanted to check if this phone number actually does exist in the list of phone numbers that we have or not, and if it is there, we wanted to actually just return the name associated to that phone number. So just actually a review of this sequential search. We actually defined a variable, we called it phone. This is just like a flag variable that we just initialize it as no, which means that we haven't found the number yet, right? And you have a loop that inside this loop we go through all the phone numbers and check and compare each one with the target value that we are looking for. And this is the line 4 that checks that target value, which actually we have it as the name, this variable name number. We are looking for this one, and so in this conditional statement you are just comparing number with each number in the list. So all of T1 through Tn are going to be those phone numbers, right? And this variable I is changing. It started from 1 and it actually goes until you reach to n. Each time we are comparing number with T index I, okay, T sub I. If it is equal, so you would say that I found it, right? You print the associated name with that, which is going to be N index I. And you change the value of found to yes. So because you change it to yes, the next time this loop will actually just stop, right? Because found is not going to be no anymore, and it will stop in the next round that it checks the condition. Otherwise, if the number is not equal to T index I, it actually goes to the else, right? And just update the value of I, so that in the next round of the loop you would compare number with the next you would compare your target number with the next number in the list. At the end, when the loop is finished, okay, when you actually reach to the I equal to n, the loop will stop, right? Either the found should get yes, which means that you find it, or you reach to the value of n. At the end, you wanted to know that if either I have found it or not. If I exhausted this search, if I actually just went through all the numbers and could not find it, or I found it, because at the end you are going to actually just jump out of the loop. If found is equal to no, which means that you haven't found the number in the list, and so you wanted to just print this message that, for example, I could not find the number in the directory. Otherwise, this part will be actually printed. Okay, so this is our algorithm. Let me just do a cleanup here. Okay, we wanted to analyze the efficiency of sequential search. Here you can see that we call this searching algorithm. We are looking for something and we call it sequential search because we compare the target number with all the numbers in the list one by one. So we just sequentially went through all the numbers and check each one. So if you actually just go back and you know, have a look at this algorithm, you can see that the algorithm actually does a couple of things. It takes the values, right? Okay, let me actually just use it takes the values, right? It set actually initialize the value of I and initialize the value of found, right? It has a loop, and it has an if condition and some printing a statement here at the end. So when you are looking at this algorithm, getting the values and initializing the numbers actually just, it can be actually considered as a fixed thing. You just give the values. The central unit of work that your algorithm does, and it would be different when you are going to have a bigger size of the input, is going to be the loop, right? The loop is going to execute a fixed, a specific actually work. It is comparing the target number that you are looking for with ti, right? This action, this comparison is something that will be repeated. So if you have 10 numbers in your list, this comparison will actually be done. For example, just assume that the number is not in the list, okay? And if the number of items in your list is going to be 10, then these comparisons will be executed 10 times, right? If the number of items that you have is going to be, for example, 1 million, the number of times that this comparison will be executed is going to be 10 million, right? Because you are going to check all of the numbers. But initialization, for example, will be a fixed thing that you always do it, but it's going to be always done only once, right? Or for example, this if condition at the end, it's not going to be repeated. So the main thing that I care about is this loop, because this loop contains some operations that will be repeated again and again, depending on the size of the input, depending on how many numbers you have in your directory, in your phone directory, right? So this is the main part of the algorithm. Let me actually just mark it here. So here the loop is going to be the central work that you will do, okay? So this is exactly where we are going to focus and talk about how much work your algorithm will do to actually finish the work and get it done. Okay, so depending on the size of the data, you see that the number of times that your algorithm is going to iterate in this loop is going to change, right? So a couple of things is going to be important for us. What is going to happen in the best case? The best case is going to be, these are actually a couple of actually important terms that I wanted to define them, then I will actually check them in your algorithm. The best case of an algorithm is going to be the case that in a scenario that your algorithm will do the smallest amount of work. Okay, so that's why we call it the best, because if your algorithm does less, it's going to be faster, right? So that's why we call it best. So the best scenario is going to be the smallest amount of work that your algorithm will do to finish the work. The worst case scenario is going to be the greatest amount of work that your algorithm will need to do to finish the work. And the average case is going to, this is a scenario that we are very interested in, because most of the time you might not actually see the best case or the worst case, but you are going to be interested in the average case of your algorithm, that on average, if if I got some random input, that the likelihood of different scenarios are going to be all normal. So how much work will be actually executed in this case? Okay, so there are going to be three different actually cases that we are going to do to analyze the efficiency of our algorithm. So now let me actually just check this sequential search and think about what would happen in the best case, what would happen in the worst case, and what would happen on the average. So if you think about this algorithm, you will see that the loop will be executed if these two conditions, both of them, are true, right? If any of them became false, your algorithm is going to stop. So there is a chance that if found change to yes, your algorithm is going to actually stop. And when your algorithm is, when the found is going to be changed to yes, if you find the number, if the number is actually equal to, if the target number that you are looking for is equal to t sub I. So what would happen if t1 is equal to the target number that you are looking for? How many times your loop is going to iterate in that case? The value of I will be 1 at the beginning, right? Then you actually compare the number with t index 1, t index I, which is going to be t1, and yes, the number that you are looking for is exactly equal to t1. So in that case, you print yes, and you set the value of found to yes, right? And you are not going to iterate more because found is going to change to yes, and your algorithm is going to stop. So the number of iterations in that case, if the first number is going to be the target number, the number of actually time that your loop will iterate is going to be only 1. And can you get anything better than this? I mean, is it any other possibility that your algorithm do less amount of work, less than this? And the answer is no. If the number is, for example, in T2, definitely the number of time that you need to iterate is going to be 2 times, right? Because when it is T1, this is not correct, your algorithm needs to iterate another time, it needs to iterate, your loop needs to iterate 2 times, and so it takes more number of comparisons. So the main thing that I care about is that how many times this condition will be executed, how many times your loop is going to iterate. So the best scenario is when the first number in the list is going to be equal to the number that you are looking for. So what is going to be the worst case? The worst case scenario means that the largest, the greatest amount of work that you would do. The greatest amount of work that you would do will be when your loop will iterate fully. It means that it will iterate n times. So that will happen when your number is not in the list, or for example, when your number is tn. Both of them are going to be the same, right? In both cases, you are going to iterate n times, and the number of comparisons here is going to be n times. So I have actually just written both of these two cases, the best case and the worst case. The best case is that when the target number is the first, will be actually found in the first iteration, your number is equal to t1, and the worst case is that when the number either is the last value or it is not in the list, right? So what will be actually the average case? So the average case means that what would happen if you randomly choose a number and you are searching for that value, right? So that value can be equal to t1, it can be equal to t2, it can be equal to t3 until tn, and it is, the possibility, the chance that it is equal to t1 or any other actual number in the list, all of them are equal, right? So if for each value there is an equal chance that they are going to be equal to the target number that you are looking for, so in that case you can actually just calculate it and say that on average the number of times, the number of comparisons that you would need is going to be n divided by 2. This is kind of actually, I can't say that this is completely a statistic, but it is a statistic. So the chance that the number that you are looking for is going to be T1 is equal to the chance that it is equal to T2, it is equal to T3 until Tn, right? So how many comparisons for this one you would need? One. How many comparison in this case you would need? Two. How many comparison in this case you would need? Three, until in this case, which is going to be n, and you just add all of these numbers together and then divide them by n. So in total, I mean, the number of comparisons that you would need is going to be, on average, it's going to be n divided by 2 number of comparisons. Okay, so we are going to come up with this table that shows that the number of comparisons, or basically the number of times that your loop will actually iterate, that in the best case is going to be only once when the number is exactly the first number in the list. The worst case, when the number is not in the list or it is the last one, and on the average case, that you don't know which one is going to be the number, but on average this is going to be n divided by 2 number of comparisons. So these are different scenarios, and we are actually just interested in these scenarios, and we wanted to compare all of these scenarios. Okay, so far we have learned something. We have learned that, okay, the amount of, the number of comparisons in this algorithm. Here you can see that we just actually just care that how many times your loop will execute or how many times these comparisons will be actually happening. Okay, so far we have found some information that on average, I need to actually iterate n divided by 2 number of times, and in the worst case, it would actually iterate n number of times. Okay, but this number of iterations or number of comparisons is not going to give me the exact number of operations that needs to be executed, right? So for example, in each iteration of your loop, you would do a couple of things. You would, let me actually again do a little cleanup here. Okay, so in each iteration of your loop, you have one comparison here, and you have some increase here, incrementing the value of IU, and so you are going to have this comparison here and this comparison here. So basically, if your algorithm is going to execute, for example, k number of times, you can actually say that, for example, I need one comparison here, one comparison here, one comparison here, and one increment here, right? So I need, for example, 4 multiplied by k number of operations. Okay, so I'm actually just multiplying this number as well. That's telling me that how much work will be executed in one iteration of your loop. Okay, but I wanted to actually tell you that if it is 4, or if it is, so let me actually just fix this before we leave. What was your table? Your table was that on the worst case scenario, you would need, on the worst average. Let's actually just forget about the best. Okay, on the worst case scenario, you would need n iterations. On the average case scenario, you would need n divided by 2 number of iterations, right? And in each iteration, you might actually just, here I have counted that, okay, I would need 4 operations, right? So in total, I can say that in the worst case, I would need 4 multiplied by n number of operations. On the average, this is going to be 4 multiplied by n divided by 2, which is going to be in total 2n. number of operations that will need to be executed, right? Okay, something which is important for me is that this difference between the average case and the worst case, you can see that the difference between them is the coefficient that you have multiplied, right? So before I just continue, I wanted to introduce something else, some order of magnitude. What does this term mean? The order of magnitude is actually just talking about the growth ratio of your algorithm, your formula. Okay, so far on the average case, on the worst case, I found that, for example, this is going to be 4n, on the average is going to be 2n. I wanted to actually just tell you that it doesn't matter if it is your formula, the amount of work that you found is going to be written as a formula, right? If it is 2n or 4n, the growth ratio of both of these two formulas are going to be linear. Okay, so here is actually just showing, this diagram is showing a couple of things for you. In all of, if you have 4n, 2n, 1n, if you have n divided by 2, if you have 10n, in all of these formulas, you can write that all of them are going to be cn, right? Because this value c is going to be a coefficient, and you know what is the value of that. This is going to be 1, 2, 3, 0.5, 10, but this is going to be a constant. This is not n. That's why we call it a linear growth ratio. And so we say that all of these numbers, all of these formulas are going to be in the same order of n. They are going to be in linear order of n, and we show it as theta of n. So this is a notation which is very important. This notation, you will see it later in COMP125, the data structure and algorithm course. You would, when you take it in COMP125, we will give a complete definition of this, and we will see lots of examples. So don't worry if you did not get the exact actually mathematical definition of that, but just know that if you have any formula that you can write it as cn, where c is a constant number, is just a coefficient, we will say that all of these formulas are going to be in the same order of n. All of them are going to be in linear order of them, and we will actually show them as theta of n. Later on in other examples, I will actually show you some algorithms that will be in order of n power 2. So you can see that there is a big difference between n power 2 and n. This is going to be called a square. This is going to be called linear. Okay, so if your algorithm is in order of n power 2, is going to be completely working in a different order than when it is working in linear. Okay, so I don't want to actually go to more details here, just later on when I talk about the selection sort, you will see that selection sort is going to be in this order, so that's going to be in a completely different order. But if your algorithm is going to be of, for example, 4n number of operations, or 2n, or n divided by 2, all of them are going to be called in the same order, and we call it theta of n. The reason is that when you are comparing the diagram of Cn, you can see that the growth ratio of all of them are the same. Although the values here and here are different, but the way that they grow, all of them, they are going to grow in linear fashion. Okay, so when later on I compare this theta order of n square with linear, you will actually get the idea that why we say that this is going to be a completely different order than this one. So okay, it's just actually the I think I'm done with this order of n and this comparison, I just wanted to tell you that this constant at the end is going to be less important for us, and we are going to actually just ignore it and say that if you have something in that actually needs c multiplied by n number of operations, you just actually just call it that, okay, this is going to take order of n or linear amount of work. Okay, so I'm going to just give it a name. So in this case, again, you will see that it's a kind of abstraction. I'm abstracting away that constant and saying that, okay, this is going to depend only on n linearly. Okay, so it will depend on n linearly. This is the fact that you should care about. Okay, so let me just see. Okay, that was the first algorithm that we discussed, and we just actually saw that, okay, so for sequential searching, the order of the algorithm is going to be n, that's going to be linear. So now I'm going to talk about another algorithm, the selection sort, and you will see there that what is the difference between an algorithm that works, an algorithm like selection sort with an algorithm like a sequential search, although they are doing completely different tasks. A selection sort is sorting the items, sequential search is searching for something. Okay, so the next example that I'm going to discuss here is going to be selection sort. So what is the task in sorting? So the sorting is going to be the task of reordering the items in a list so that the order of them are going to be, for example, if there are some numbers, they are going to be in alphabetic order. Or for example, if there are some letters or if there are some names, they are going to be in alphabetic order, or if there are some numbers, they are going to be in increasing order. Okay, so in this way you are sorting it, right? From the smallest one to the largest one, or alphabetically from A to actually Z. They are sorted in alphabetic order. So we are going to give them a specific order. So we sort them. So here, in this actually the sorting algorithm that we call it selection sort, the idea is that this is actually, it has been covered as, the figure 3.6 in your textbook. And the whole idea of this algorithm is that we go through all the actually numbers at the first, all the items in your list. Just assume that all of them are, for example, number. Go through all the numbers in your list and find the largest item. Okay, after you find the largest item, just swap it and put it as the last number in the list. Okay, and in the next time, just because you have actually already found the largest item, forget about that, put it aside, and among the rest of the numbers, look for the next largest item, then put it as the index, for example, n-1. Okay, and you will just repeat the same action again and again until all the numbers will be at their actually specific position. So this is the algorithm. Just assume that the input for your algorithm is going to be a list of n items. You can just think of it as a list of n numbers, and you need to also define a variable which is like a marker that tells you that which part of the list hasn't been sorted, and so you just updated that. Let me actually just, instead of going through the algorithm directly, let me just run the algorithm, simulate the algorithm over a list of numbers here that I have. Then you will actually just understand that how it actually works. So at the beginning, the marker is going to be actually just marked at the end of the list, which basically means that nothing has been sorted. Everything from the market going on is going to be sorted, right? So if the marker has been set to the end of the list, it basically means that nothing has been sorted in your list. Okay, so you can see that actually I just put, initially we set the marker to actually refer to the end of the list, which means that nothing has been, let me actually just write down this example underneath the figure, the algorithm, then you can actually just, we can go through it at. So 5139, so this is the list, 5, 1, 3, 9, and I guess that the last one was 4. Okay, 4. Okay, think about it in this way, that I would have a marker that the marker will, let me use a different color, that's going to make it better, I mean more readable. Okay, let me 5, 1, so this is the list, 5, 1, 3, 9, and 4. This was the initial list that you get, and you set the marker at the end of the list. This is the first step, right? Before the loop. Then check the loop. The loop is has a condition that says that until unsorted section of the list is not empty. Okay, so the marker actually shows that the end of the list as from this point on everything is sorted. So the rest of the list hasn't been sorted yet. Okay, so this part is going to be unsorted part. Unsorted. So the loop will iterate until the unsorted section of the list is not empty. So the unsorted section of the list here is going to be 5. So far nothing has been sorted in the list. Okay, so then what does the loop do in each iteration? It will find the largest number in the unsorted section. Okay, so the unsorted section here for me is going to be from here to here. This is unsorted section. Find the largest item in unsorted section of the list and exchange it with the last number in the unsorted section of the list. And then you can actually move the marker just to the left, one position to the left. So so it's just decrease the unsorted part. So first let's find the largest item. What is the largest item? The largest item in unsorted part is going to be 9. Okay, so the action that I will do is that I will change it, I will exchange it with the last item in the unsorted part. So by the end of the first iteration of the loop, the list is going to change like this, 4 and 9. Okay, so what would happen here? The marker will refer to here. So let me actually just use a different color. The marker would refer to here, marker. So it means that from here to here is going to be the unsorted part. Okay, so still the unsorted part is not empty. I will actually just continue. In the next iteration, again, you find the largest number in the unsorted section. What is the largest item in the unsorted section? The largest item is going to be 5. You would exchange it with the last number in the unsorted section. So you have to exchange it with the 4. So by the end of the second iteration, your list is going to look like this: 4, 1, 3, 5, and 9, and marker will be updated. Okay, and this unsorted part is going to be here. This is the marker. Okay, still the unsorted part is not empty, so you continue. In the next round, again, you find the largest item in the unsorted part. This is going to be 4. You would swap it, you would exchange it with the last item in the unsorted part. So, and so in the next iteration, by the end of the second iteration, let me use a different color. By the end of the second iteration, you would have the list in this form: 4, 5, and 9. The marker will be updated to here, and the unsorted part is going to be this part. Okay, still the unsorted part is not empty. Okay, so in the next round, you would again find the largest item in the unsorted part, which is going to be this one, right? And you would exchange it with the last item in the unsorted section. So by the end of this loop, this iteration, you would have the list in this form. Okay, and the marker will be updated to here. And this is going to be the section, the unsorted section. So, okay, so the thing is, in the next iteration, when you actually have just one item in the unsorted part, you can stop also, but let me actually just follow this algorithm here. The last item, the unsorted part is not empty yet, so you find the largest item. The largest item is going to be the item here, and when you are actually just exchanging it with itself, it's going to actually just be here, right? And the marker will update it to here in the next iteration, and the whole list has been sorted. No, you can actually see that the list is going to be sorted, and the marker has been updated to here, and everything has been sorted in your list. Okay, so there are actually a couple of things about this this algorithm. I hope that you understand that how the algorithm works. It has a marker that actually shows that which part of the until which part of the list hasn't been sorted yet. In each round, you will find the next largest item in the unsorted part, and you just swap it, you just exchange it with the last item in the unsorted part. Okay, so you have a loop, and you have a couple of actually things that you need to do in each actually iteration. Okay, so here the if I'm going to analyze the algorithm, which means that I wanted to measure how much work the algorithm would need to execute if I am sorting a list of size n. This example was of size 5. I just wanted to know that if it is of size n in general, how many actually work it would need. So you have a loop here that actually iterates. How many times it will iterate? You can see that you have a marker, that the marker has been initialized at the end of the list, and in each iteration it will just update it by 1, and it will be decreased once. So this loop will iterate n times, right? And it doesn't matter what is inside in your data. I just wanted to tell you that there is the best case scenario and the worst case scenario, in this case, they are going to be the same. So because of that, there are not going to be any average case. So both, if whenever the base case and the worst case are the same, you are not going to have an average. You have, but the average is going to be equal to the best and the worst. There is no difference. All of them, they are going to be equal. So the first thing is just know that the loop is going to iterate n times, which is going to be the number of times that the marker is going to be updated. But not only the loop is important for me, there is a specific thing happening inside the loop. And that is this line, selecting the largest item in the unsorted part of the list. How you can find the largest item in the unsorted part of the list? You need, you already actually know from the algorithm in chapter 2 that finding the next item need a loop. This is not going to be a simple operation. Okay, the computer does not know how to do this one. So to find the next largest item, you basically need to search for it, and you need to compare. You need to actually start it from, for example, here let me actually use a different color. When the unsorted section was this part, when you have it 5 item on this unsorted section, you need n number of comparisons to find the largest item, right? You need to compare, for example, the maximum number with this one, then you compare it with this one, this one, this one, and this one. So finding the next largest item will depend on how many items you have in unsorted part. When you have n numbers in unsorted part, it would need n number of comparisons. When you actually just update the marker and the unsorted part became n minus 1, the number of comparisons that you would need to find the largest item is going to be n minus 1. Then here it's going to be n minus 2. So until it actually just reaches to 1, the number of comparisons that you would need to find the next largest item here would depend on the size of the unsorted part. So at the first it's going to be n comparisons, then it will be n minus 1, n minus 2 until 1. So this is going to be the total number of comparisons that your algorithm will do in this line to sort your list. So I just wanted to emphasize that this is the main unit of work. So you need to add all of these numbers. And so far, from that Gauss formula, you know that the summation of integer numbers from 1 to n, so you see that these numbers are going to be from 1 to n. It doesn't matter if you count it from n to 1 or 1 to n. The summation of them both are going to be equal. The summation is going to be n to n plus 1 divided by 2. Okay? This is going to actually tell me something. The number of comparison is going to be, if I just simplify this, the number of comparison is going to be 0.5 multiplied by n power 2 plus 0.5 multiplied by n. Okay, so you see that here for the selection sort, I am getting a completely different formula. Remember when we talked about the sequential search, that we found a formula that was c multiplied by n, and we said that that constant is not important, and we say that, okay, whatever is the c, if it is constant, if it is, for example, 10, if it is 0.5, we are saying that this is going to be a constant and your algorithm is going to be in order of n, in order of linear. So here for the selection sort, our algorithm is going to be in order of, your algorithm is going to have this number of comparisons, right? this is going to be in order of n power 2. Although I also have this term which is n, but you will at the end see that this term is going to be way smaller than this term. So we will say that this term is going to be the dominant term, right? So at the end, our algorithm or selection sort algorithm is going to be done in n square, in the order of n square. And we write it as theta of n. So we call it order of n square. So now let me actually just compare the algorithms that works in n square and linear, in the order of n square and in the order of linear. Look at this table. This table actually just summarizes the comparisons between those numbers that works in, not this one actually, basically this one. When you are comparing, when I'm saying that n power 2 is the dominant term, just compare these two. If you have an algorithm that works in order of n power 2, you see that here it actually just emphasizing on this fact that the constant, even if the constant is very small, at the end n power 2 became very large, and that algorithm that works in n square is going to take more amount of work than the algorithm that works in order of n. Although, for example, the constant here 100 is way bigger than the constant here, which is 0.00001. Okay, so those algorithms that work in n square order, in the order of n square, they are going to take more time than the algorithm that works in linear order. Here you can actually just see the comparison between these two type of algorithms. I mean, using the diagram. This is the n square diagram, this is the linear diagram. You can see that after just, for example, point 1, the order of the growth ratio of n power 2 is going to be much faster than n. What does this mean? When the growth ratio is much faster, it means that, okay, the amount of work that needs to be done by the algorithm that is going to be in order of n square is going to be much more than those algorithms which are linear. And here it actually just compares the difference between the coefficients. So although this one, n power 2, has been multiplied by a small actually coefficient, compare it with 10n, which has been multiplied by a large coefficient. It just tells you that it doesn't matter, the coefficient doesn't really matter at the end, because at some point, at the end, 0.25 multiplied by n power 2 is going to be much larger than 10 power n. And the growth ratio of this diagram is much faster than the growth ratio of this diagram. And this table is actually just even showing the more extreme of this comparison, that this coefficient for n power 2 is very small comparing to considerably large number. Although for the small numbers, this one is going to be larger than this one. But it just tells you that when the value of n grows, when n approaches to infinity, this number became much larger than this number when you actually just calculate it, right? So you can see that at this point they are going to be equal, and then after this point, for all the values greater than 1 million, this term is going to be much bigger than this term. And why we are saying that we care about the larger value of n? Because when you are running an algorithm, if the size of the input is very small, anyway your algorithm is going to work very fast. If the size of your, for example, if you have just 100 number of items to sort, it doesn't really matter then what is the efficiency of your algorithm. Your computer, the current computer that we have, they are going to be too fast that they can do it in fraction of a second, right? So you can't even actually notice that how much time your algorithm would take. The computer will execute it in a blink, so you would actually even notice the difference. But this is important because when you are writing an algorithm, most of the time you would think about the large sizes of the input. Okay, so you would think about the large size of n. So that's why we would say that this algorithm is going to work worse. This algorithm is going to be a better algorithm, right? We definitely are going to prefer the algorithms that has linear, the algorithm which are in linear order than the algorithm which are in n square order. Okay, so if you have an algorithm B which is 110, you are going to prefer this algorithm over these algorithms because the amount of work that this one needs is going to be less than the amount of work that this algorithm needs. Okay, so basically this is the all of the discussion about so far until the section 3.3, which is going to be the part that we are going to cover for this week. So just make sure that you would read section 3 up until the end of chapter 3 up until the end of section 3, and do the exercises for section 2 and section 3 as a practice.